Hey everyone, my name is May, and today I'm going to talk about the fairness of fairness. All right, next slide. So the structure of my talk is going to go in as this. We'll start with why fairness matters, go into a grounding example on insurance, and then go into how this example translates to every step of the machine learning life cycle. So ultimately leaving you with some tools and resources so you can take away and put these resources into your own practice. So why care about fairness? I mean, if you ask anyone if fairness is important in ML, they're probably not going to say no. I mean, you'd be a terrible person. I'm kidding. But if you say how you're doing fairness, the answer is going to vary. There is really no exact answer of how to do fairness right now. It's a growing field, rapidly changing research. By the FTC, previous commissioner, defined fairness potential economic harms of AI as threefold. So number one, denial of benefit. If we don't give someone insurance to ensure their family's stable safety in the future, I'm not trying to sell you insurance here, that's a denial of benefit. An exclusion from opportunity. Let's say if they don't even see the offer. Let's say they don't even see the job offer to begin with. That's an exclusion from opportunity. Let's say if they're paying a greater price, but for the same product or service, that's negative predatory targeting. So these are issues that we need to solve and harms that can potentially imposed by AI. So in insurance, it's regulated, it's a very regulated field. In Canada, it's regulated by OFSI, the Office of the Superintendent of Financial Institution. They report to the Ministry of Finance and is a federal regulatory body. But in the US, it's a little bit more fragmented. Every state has its own commissioner, which causes a lot of more debates to be had, and it's always constantly changing as every state tries to regulate it differently. A study by the FTC in 2007 analyzed difference of racial groups and how different racial groups are getting insurance. And on the lower percentile were the African Americans and the Hispanics, and that triggered a number of more research saying, okay, let's look at racial groups as a protective factor and see what we can do here to equalize out the impact. To ground this talk in insurance example, I'll tell you about what my team builds. We essentially automate the giving a calculation of risk of insurance, someone's mortality risk. So in life insurance, how likely are you to die? And features here, age, gender, and income are sensitive features, the ones in yellow. And personal disclosures we take in, see like, okay, do you like skydiving in your free time? We take that in as well. Third-party data like Milliman give us a risk score. Your credit rating, we take that in. A smoker status, we predict whether if someone might smoke from their medical records, from what they're disclosed. If we have a phone recording of them, like hello, we can kind of tell by their voice. We're trying to do that as well. Medical claims model, we have a specific models, sub-models, I guess, that goes into this larger model that see what's their medical claims. This more applies in the US. Driving record, if the DUIs, insurance history, if someone's disclosed, let's say, any information to another insurance company and they try to apply with us and say something different, we can correlate that and see what the difference is. Any public records, careful we put on Facebook, activity data as well if we have wearable data. And ultimately we come up with a risk score. So if the person deems too risky, then they go towards manual underwriting. If not, then we give them a decision on the spot. So every single problem I've mentioned there goes into this ML life cycle. You determine your problem, to collect data on your problem, feature engineer, train your model, select your model, optimize it, evaluate it, and then deploy and monitor it, and then this starts all over again. For this talk, I'm going to focus on these two aspects and go a little bit deeper in them. So selecting your model, training your model, and then evaluating to see why that works. Does it work? So let's start with this one. The first question after you select your model, maybe it's an XGBoost, maybe it's something else, say what do you care more about in your model? And I'm talking more about fairness metrics here. Now, of course, your accuracy you're gonna take care of that, but what about fairness metrics? What do you care more about? Do you care more about representation? Let's say, I'm gonna use the example biological sex. And do you care more about, say, giving insurance to the same amount of women than men, or the proportion of insurance, 50% to women, 50% to men that applied? Do you care more about that? What if there is an imbalance in your subgroup? Let's say only 2 women apply and 100 men apply, or vice versa. It's not going to be fair, right, if you only choose the same amount or equal numbers. So maybe you care more about the harms done. So what's the mistake I'm making between different subgroups? So women, different racial groups. Am I making more mistakes on African American or on Caucasians? So that leads you to a disparate error. And the next question to ask is my model punitive or assistive? So let's go back to the problem identification. So if it's a punitive model, your model declines applicants. If it's a punitive model, you want to see, okay, how many applicants has my model declined? And that will be your positive class, right? So if it's a small population, you want to say, okay, take a look at everyone I've declined and see what percentage of that is a mistake. So that's your false discovery rate, or FDR. And if your hit rate is pretty high, you can just use your false positive. If your model is assistive, say if it gives scholarship or it gets someone insurance faster, then it's the exact opposite to that. So say, who am I not helping? And see how many of those is a mistake. And that's your false negative. So now we have a metric. What do we do with that metric? We can take that metric and say, pin it against these subgroups. So in this case will be females and males, or if you have multiple groups, say different racial groups, you take the majority group and you divide that, so the ratio, divide that by the minority group, or you take the difference in the majority group minus the minority group. So if the ratio, you want both sides to be almost equal, so you want it to be as close to 1 as possible. If it's a difference, you want it to be as close to 0 as possible. Now we have an optimization problem. Excellent. What we can do now is optimize for both accuracy and fairness. So think of this as a hill climbing scenario with Lagrange multiplier. You can see that F, it would be the hill of the fairness, and the slice would be your model accuracy. And you want to optimize for both now. So great. You can actually use this, you can use a package called FairLearn to do this quite easily. You can program your own, and I'll put a slide with all the resources at the end. So you can log your model metrics in MLflow, and you can get different versions of your models to get the best model possible. Excellent. So now you have a fair and accurate model. Usually there's a trade-off between the two, but you have a couple. Now you want to explain why it works. So you might have heard of SHAP values, so Shapley additive explanation, which explains which features in your model best, decides the attributes to the model decisioning. So in this example, S5 is a feature, one of the features I've shown. However, you see sex is also on top there. So sex also contributes very highly to the model decision, and we don't really want that. So what do we do? In our team, we take this original model and we put it aside. We train a highly, highly biased model. And why do we do that? We train a highly biased model only on sex and on age. And now we take that model, take the score from that model, use the original model's output divided by the highly biased model to get rid of the effect of these bias or the sensitive features. So, but there are some critiques I have for SHAP. For high dimensionality, it's hard to, for large data sets, very computationally intense. We have hundreds of features. It's going to take a while to run. So what we do is take a subset of the features and we run SHAP on that. So we can quickly iterate And then finally, maybe on your final model, your final version of the model, you can run the whole of your features. It's best for tree models. It's locally interpretive. It doesn't account for collinearity, so it assumes the features are independent and it's sensitive to change as well. There's other methods like Lime is also a Python package, just like SHAP, that you can use it's called locally interpretable model agnostic explanations. Here you see the red cross. What we're doing is getting the robustness of that locally, of that feature, of that instance. So we're perturbing that instance to see, okay, how can we explain this instance locally and with a linear model instead? How this applies to fairness is you can perturb, say, a male instance and then say a female instance or different racial group instances and see how stable is your model on each of your subgroups. Again, I have also critiques for Lime as well, similar to SHAP. It's best for local interpretations. Stability of explanations will depend based on your model. So going back. Yeah, so Lime tells you, okay, how much can I perturb a feature, a point such that the model decision does not change. And counterfactuals is the exact opposite to that. So what do I have to do to this point such that the model decision does change? Let's say we decline someone. Say you're not suitable for insurance right now. What do you need to do? You need to lose some weight and get a job. And then we'll maybe come back and we'll give you insurance. So in here you can see the original input. You can say, okay, what does this person need to do to, get on the other side of the model decision? And there's going to be multiple things that can be done to change the decision. And that's called the Rashomon effect, where you can perturb this point differently, and lots of things can be done differently to get an ultimate different decision. So how this applies to fairness is, say if you have a male applicant, if the only thing that's changed is the gender or the biological sex, and the model decision changes, maybe your model is biased. There's also other factors that come in here. So you can use DICE. It's DICE-ML. It's the Python library created by Microsoft. You can use that in your model and essentially get, you can set certain features that you can change. Let's say age would be pretty hard to change. You can't tell someone to get younger, let's say, but their weight might be a bit more malleable there. But there are factors that come in. Let's say if you tell someone, okay, go and lose weight and get a job, and they do that and then come back, you're like, oh, sorry, you're too old now. That's kind of, that breaks trust, right? So you might want to consider how you're using this, how you explain it to people. And we can talk more about the aspect of using LLMs here as well. We've been playing around with it and to see how we can explain a decision in natural language to an applicant. We can talk about that more during Q&A. So what if we have a bad actor here? And the whole talk is, okay, the fairness of fairness. Maybe this is not really fair. What we're doing here, counterfactuals, SHAP line, maybe it's not really fair because recent papers have shown that these can all be attacked adversarially. This paper from Hema L's lab from Harvard, she has a great research group, talks a lot about fairness research. And start there if you want to get into the research space. Saying that, okay, if a data scientist can see how much noise, let's say, to perturb a point such that the decision will change, they can essentially lie to the regulators and say, okay, this is how much noise to add, this is how much not to add to a certain population or subset, and prove that the model is fair when it actually isn't. So that is something to consider as a regulator. I don't know if anyone's in the audience, to essentially, you have to think about how certain information is presented and if you are being manipulated. So going back to the overall life cycle practice, The problem formation we talked about. Define your problems, very important. See if your model is punitive or assistive. And then collecting the right data to make sure that the data you train on is the data that you're actually using the model on in production. And then feature engineering to avoid any proxies. Let's say, postal code and income is actually, they're proxies to each other and also proxies for race as well. So determining if there's any collinearities and being aware of that. And we talked about model training and selection and evaluation. Deploying your models and communicating what your model is actually doing to the people who are using it at every stage, like the business people, like the regulators. What we do at Munich Re, we create model cards to communicate these. Like for each model, we have ML flow runs tracked on Databricks to essentially get a versioning history of each model and how they were developed, what kind of data sets they were used, and so, as well as the business aspect of it, like what we intend for this to do. Monitoring is key as well. We use a vendor. You can also build or buy. Taking a look at, this is probably the lowest hanging fruit for most people that want to just get into fairness to begin with, to monitor what's your distribution of the data coming in. So separating it by subgroup. How many male applicants do I have? How many females do I have? What's the percentage I'm rejecting and accepting for each? Or for other subgroups as well, to just taking a look at that can help you understand what is my production population and how that's different from my training population is going to be your best, your easiest point to start for most people. And of course, maintaining this whole process, so updating your model with new data that's coming in, and then periodically reevaluating this whole process is key. So here's some tools that I mentioned. Phoenix is one of the newer ones. You can, if you're a data scientist, you can actually use Phoenix inline in your notebook. It's quite nice. It's free. These are all Python libraries. FairLearn, you can install, pip install, or poetry add, whatever you want. And you can use use FairLearn to do the optimization feature that I mentioned, and calculate a lot of the fairness metrics like equalized odds, demographic parity, and there is also you can use a widget to do it inline as well. If you're a data scientist, it's really easy to do that. You can use MLflow to track your experiments, to track it all in Databricks or whatever else you use. And SHAP, Lime, and Dice-ML actually for your explanations. So in conclusion, thoroughly consider the tools that you're using, what the tools really mean, why you're using the tools, and who's providing you with the answers. Have continuous conversations. We have been having conversations with regulators for many years at this point, and the conversations are still being had and regulations still being developed as of now. So it's key, whatever industry you're in, whether regulated or not, to continuously talk about it with the stakeholders. And also be careful of the language that you're using. A lot of what we talked about just now it's not English, the math is not English to regulators, and it's key to translate that into something that people can understand outside of a practitioner's level of expertise. And also ultimately being stewards of fairness as you are in your seats, to be aware of what you're doing before you turn it into a pipeline, turn it into an automated process, to be aware of what you're doing before automation. Thank you very much. Oh. Okay. Thank you. Oh, sorry, there's one behind. Oh. Should I take the question? Okay, he's getting a mic.
Thanks very much. That was really informative. It's also very, very topical because a lot of people probably know the European Union is working on the world's most comprehensive regulatory regime governing artificial intelligence. It just passed a major step a couple hours ago. I think it's at the European Parliament or whatever, one of the big steps. It looks at a lot of stuff, like certain things are banned in AI, such as facial recognition, social credit scoring, and then certain things are heavily regulated, such as they use the term like algorithms, applications that have life-changing consequences for people, such as employment, education, criminal law, and perhaps insurance. So you mentioned LLMs in terms of providing transparency and helping assess, monitor, improve bias. I'm wondering what other applications you see for LLMs in this area.
Yeah, thank you for that question. So the question is LLMs and how we're using that in fairness. We're currently in the research and development phase for that and exploring how we can use it. But essentially, you can take the outputs from everything that I just showed you, provide a context for your feature, like say like SHAP value for this feature is 1.3. This is the value of the feature, the actual feature, and then listing all your features, and then feeding that into an LLM and asking it to explain what does that mean to an applicant. And one step beyond that is how can the applicant reach that point? Let's say, how can they lose that weight? How can they, get a job? Okay, that might be a little harder. But see, it's a gray area right now. But how can they go ahead and do that is also the next step. Yeah, thank you.
Hi, that was a really fascinating talk. Thank you.
Thank you.
I was wondering how you've been handling sensitive features in production. There's often lack of access to PII data or things of that nature, and also some of those metrics do require understanding of the ground truth in order to calculate error rates, which is obviously not available in production, or else there'd be no need for inference. So can you elaborate on those?
Yeah, as an insurance company, we luckily have all the access to sensitive data. So that access part is not, I guess, a barrier for us. But you're right, like getting the actual ground truth, as if did someone actually die after we give them insurance? We're not getting that at evaluation prediction time. So the way we are monitoring is just simply clustering the monitoring aspect I mentioned, like monitoring how production data is changing from test data. That's the best way to monitor how the people are changing right now, and all the positive and false negative rates are being done at model training and evaluation time. Yeah. Thank you.
Hi, May. Great, excellent talk. My question is, I used to be a licensed life insurance agent and mutual fund agent with a very big technical background. A lot of the reasons why people would look to insurance is to have some kind of opportunity for the future generation. But sometimes a lot of people don't have access to equality of outcome, where insurance allows them equality of opportunity, or should. How do we look at the bigger picture of models that are used to assess someone's ability to qualify for insurance without considering all of the other tertiary impacts of, say, they disqualify for some reason, in terms of bias, for example?
First of all, you should come work with us.
Okay.
I think the question was, how do we evaluate a larger number of people?
That's right. Like the bigger impact of these models that can have a huge impact on their ability to get insurance, right? To cover their lives, to cover the foundation of all of the things that they've built financially.
First of all, they have to apply. How do we reach them? I think is one aspect. Like the second harm I mentioned, if they don't even know about it, like they're not even educated about it, that's one. We can't even reach them. So I think figuring out a better way to market towards them would be one way of access. Other than that, to to get like a full understanding of who they are. Like, okay, so this is actually another application of LLMs, is where if a person doesn't understand the question being asked, if they have a language barrier, they don't speak English or French or whatever language we're offering it in, then they can't really understand the question. And this goes to other, applying for like loans as well. So using LLMs to, I guess, clarify a question is another application. So if you have, or even to translate that into different languages. So if you have a question and person wants to clarify what this question is really asking, this, say like, okay, what about smoker status? And say, what do you mean by smoke? Like, what do you mean by smoking what, right? Like that could be like a reflex, I guess you call it reflex question on that question itself to clarify. So that's another way
Thank you.
to answer your question. I know there's one over here. Did you have another?
Thank you so much. May, I was wondering, when you talked about like the counterfactuals that you showed, so in terms of kind of thinking of the edge cases of your model, like is there a kind of like a pipeline or a way that your team thinks about it? So like how do you think of the case, like as many cases as possible, and then maybe you run into an edge case every once in a while on the different results, unpredictable results that your model returns?
Can you clarify on an edge case? Like what kind of edge case are you?
So like for example, when you were saying like, oh, okay, first you have to lose weight and then you have to get a job. Oh, but you're too old now.
Yeah.
So like I'm thinking like in terms of things like that, like is there kind of a way that you test the parameters of your model to see, okay, so what are the results that it's returning, and then what are some maybe things that we're not thinking about? So I guess your unknown unknowns. Is there a way that you approach?
Yeah, no,
that?
like what a person can change. Like say it'd be easier for someone to increase their income than lose weight. Like maybe it's for this person, right? It'd be for that person to be the exact opposite. So yeah, that's a really good question and something we're still developing internally. But yeah, that's. You want to provide people with different options, and that's where LLMs can come in, where the person can you give me another option, and then we provide the other option. So that's a way, and you also want to take into consideration like the time factor as well, like if to provide them with the answer with time included. So like say in 2 years, if you do this, then maybe the results would change. So providing that context so they don't become too old and then that result doesn't apply anymore. So that's, yeah.
Okay, no, thanks. Thank you for that.
Yeah. Yeah, did you have a question?
Hi, thank you for the great talk. So my question is, how do you determine if something is an unfair bias or is just a natural characteristic of the data?
Sorry, can you repeat?
How do you differentiate between unfair bias and bias that's actually a characteristic of the data?
Characteristics
Of the data.
Of the model or?
Of the data. Like for example, you can have one bias.
Bring
that's
your mic in.
Okay, sorry. So my question is, how do you differentiate between unfair bias and bias that's from how the data actually behaves?
How the action behaves.
How the data actually is.
Oh, how the data is.
Yeah, compared to like.
Okay, I see. So if the model is being biased or if the data is being biased?
Yes.
So yeah, I think that comes with the data exploration aspect to begin with. So visualizing your data, calculating metrics on your data before you model, I think would be the best way to discover any biases in the data to begin with. Like, is it biased to one side? Like, is it there's different, I guess, moments of the data. Like, you want to take a look at like the first, second, third, fourth moment of the data. Is it skew? Is it kurtosis? Is there, if the different populations are actually differently, spread in your database, that's really important to look at. So taking a look at those data metrics before you model would be number one. Yeah.
Hello. Yeah, I had a question that we do a lot of things to remove the bias, let's say from the sex attribute. but why can't we just remove that from our training features?
Yeah, really good question. And that's something that we have explored as well. Like do both, to explore to see which one is more fair. The thing is, there is collinearity between the features. So let's say if something else also has a gender-based, like sex-based, flavor to it, then by dividing, you're actually canceling out some of the collinearity effects as well. So that's our theory, at least. Yeah, we use a gamma model to do that. Yeah.
Hi, thank you. You've explained very well about the protected attributes and fairness in direct-to-consumer businesses, but I'm curious about your thoughts on business-to-business fairness and what might be protected or sensitive attributes on an organizational level.
Wow, that's a really insightful question. Like what are sensitive features to an organization? That I actually don't have experience with, so I can't really say for certain. But if you take a look at the makeup of that business, like what kind of proportion of that business, I can't really give you a great answer for that right now. But thank you for that question. Yeah, there's one more up here.
Okay. I will.
Hi, great talk, first of all. And second, so you talk about, the collinearity kind of issue, right? Of like, okay, we have kind of, with like something that would be like income versus like activity data, someone, or like job and weight loss, it tends to be, correlated with income and that sort of thing. So you have all these features that are in essence correlated with each other. Do you end up in a space where you're like, we're doing, because you said the dividing kind of these things out tends to be something that works well to you. Is there a kind of point where you almost, that stops working because there's so many of these kind of features, and kind of what's your strategy of dealing with that, or even things that are kind of, I guess, multi-collinearity with each other? I find it to be a really interesting problem, and I'm wondering, have you guys started to explore that, and how?
Yeah, no, that's a good question, and I think a lot about that too. Like, I guess if we take a step back, like in insurance or any modeling in general, like we are trying to be biased, right? We are trying to see who is eligible and who is not. So the whole point is to be biased, and then we're trying to say, okay, we don't want to discriminate on certain protected features. So the best way is to dividing out that concept to that you're canceling out that effect. But ultimately, I think it comes down to the disparate error. So that if this person, so you just want to equalize on the error that you're making on different groups, instead of saying, okay, I'm going to get rid of all the relationships in the world, and which is impossible. Like, the world is so connected. We're a multi-connected world, right? And everything is dependent on everything else. To be philosophical a little bit. So the best way, I would say, to go back to that error aspect and, to look at your data. Do you trust your data? If you trust your data, then you can trust your error rate. And then you can trust your error rate, then you can equalize on them and optimize for a better and fairer world.
Yeah, that makes sense. No, that's super cool. And identifying, are there things that are like, we shouldn't be looking at all, because regardless of if they're an error, are they just going to produce inaccurate results, and kind of which ones even should be on the error side versus the data side. Super interesting philosophical questions. Awesome.
Thank you for your question.
Yeah, thanks so much.
Okay, thank you.